Now, the last thermodynamic process is a special polytropic process. This type of process can be visualized by the expansion or compression of an ideal gas inside a water-cooled or air-cooled piston cylinder arrangement. To start with our analysis, let us again assume that heat will be transferred into the gas. As expected, the gas will expand inside the piston, causing the volume to increase and the pressure to decrease at state 2. But what is special about this process can be seen in the TS diagram. Even though heat is transferred into the gas, its temperature continues to drop at the end of the expansion process at state 2. The reason behind this is the presence of the surrounding cooling mechanism. Whether we use air or water as our coolant, this cooling mechanism tends to lower the temperature of the gas during the heat addition process. As a final note, if we tend to reverse the process, that is, if we have a polytropic heat rejection process with compression, the shapes of the PV and TS diagrams are going to be the same, except that the positions of states 1 and 2 in the graphs will not change. The three forms of the PVT relationship in polytropic process are very similar to those for isentropic processes. On the other hand, the non-flow work can be found by evaluating the area under the PV curve. We will arrive at this form of the equation, which is quite similar to the non-flow work for isentropic process. The only difference is that the specific heat ratio K in the equation is replaced by the polytropic index N. The approximate and exact solutions for the change in internal energy and the change in enthalpy are just the same as the ones in isobaric and isothermal processes. Now, the amount of heat transferred can be computed using an exact solution or an approximate solution. The exact solution involves using the non-flow energy equation, but the change in internal energy should be based on the values of the specific internal energy of the gas coming from its property table. Based on the other hand, the approximate solution involves using this derived formula. C sub n is the specific heat value that we use for special polytropic processes, and this can be computed using the formula shown. Now I will show you how to derive this formula. The approximate solution for finding the heat transferred during a special polytropic process can be derived using the non-flow energy equation. Now we can replace delta U in the equation by mcv delta T and the non-flow work by the formula that we presented in the previous slide. Then we factor out mass and delta T from the two terms. After that, we now add the two remaining terms inside the parentheses. By doing this, we will arrive at this form of the equation for Q. Now remember that the sum of the specific heat ratio at constant volume and the ideal gas constant is just equal to the specific heat ratio at constant pressure. So we replace the sum of these two terms by C sub P. Furthermore, we can also express C sub P as the product of the specific heat ratio K and the specific heat at constant volume Cv. Therefore, we will arrive at this form of the equation. Finally, by factoring C sub V from the numerator, we will now arrive at the formula for the specific heat ratio for special polytropic processes. Now, the change in specific entropy can be approximated by considering the polytropic specific heat sub C sub n to remain constant. This will allow us to arrive at this formula for delta S. We can also replace the ratio of the final temperature to the initial temperature inside the logarithm by the ratio of the pressure or the ratio of the volume, using the third form of the PVT relationship that we discussed earlier. The exact solution can be found using these formulas. The one at the top will give you the change in entropy in a per unit mass basis, while the one at the bottom will give you the change in entropy in a per unit mole basis.